Hello friend, welcome to the course Essentials of Data Science with R software. So you can recall that in the last lecture we had considered the probability mass function of a geometric distribution. And beside those things we have considered couple of probability mass functions, and there is a long list of the probability mass function that can be considered, but definitely I have to stop somewhere. I have to choose some of the important probability mass functions that I can give you in this course. So now from today I will switch to the probability density function, which are defined for the continuous random variable. So now in this lecture we are going to consider the uniform distribution. Now you can recall that we also had considered the uniform distribution in the case of discrete random variable, and similarly we also have a uniform distribution for continuous random variable. So in this lecture we are going to talk about the uniform distribution for the continuous random variable, and we will see how we can handle it in the R software. But just before, because we are going to now start with the continuous random variable, although we have discussed it in detail, but I will try to give you a quick review that how these continuous variables can be observed and some minor details about them, and then I am going to start the uniform distribution. So let us begin our lecture. Okay, so in case if you try to understand how the observations on continuous random variables can be obtained. So let us try to take some example, right? Suppose a part of machine is manufactured in a factory every day, right? And suppose some dimensional length on is measured, means some component, some part whose length is measured. Now, do you think that when these manufacturing is happening, all the parts are going to be of the identical length, exactly the same length? Means in practice there can be a small variation in the measurements, and which can be due to many reasons, right? Such as there can be some vibration, temperature fluctuations, operator differences, calibration, cutting tool wear, bearing wear, raw material changes, etc., etc. And these are random variation because they are not in our control. Suppose there are two operators who are trying to build up some part. Do you think that they are going to produce exactly the same thing? Certainly not. So now let me try to take here some examples of the continuous random variable. So let there be a variable capital X, which is continuous in nature, and this X is indicating the current measure in a thin copper wire in milliampere. Now you know that whenever there is some current flowing in a wire, if you try to measure the value of the current or the presence of the current at a particular point, that will be changing throughout the wire. So it is very difficult to make a statement like at this place the value of the current is 12 milliampere and at this point the value is 13 milliampere. Rather, making such statements, we can assume that the range of the current in the wire is between say 0 and 20 milliampere. So the range of the random variable X will be between 0 to 20 milliampere, and that will mean that the current at every point placed in the wire is between 0 and 20 milliampere. Right. Similarly, if you try to see the packets of a chemical compound, suppose it is written on the packet the weight of the chemical is 150 gram, but if you really try to measure it, that may be 150 gram or 151 gram or 152 gram or 152.5 gram and so on. So there will be some small variation that will be present in real life. So one can make a more realistic statement that the net weight in a packaged chemical compound is between 150 and 160 grams. Right. Similarly, you have seen that whenever we go to a grocery shop and we try to look into the bottles of the shampoo, although it might be written outside that the contents are 375 ml, but if you really try to measure accurately, this value may be somewhere between say 374 milliliter to 380 milliliter. And that is due to some random variation because the packaging is being done by some automated machines. right. So, one can say that the volume of a shampoo filled into a container is uniformly distributed between 374 and 380 milliliters. Right. So, in such experiments, the measurements are represented through a random variable x, and these random variables are going to assume some values. So, now in such a situation, instead that we assume that the x takes the fixed value at some particular point, it is a better option that we assume that the random variable x is taking the value interval, right, and this interval is of real numbers. So, what we assume that the measurements are represented as random variable x, and it is reasonable to model the range of possible values of x with an interval of real number, right. And we know that a continuous random variable is a random variable with an interval of real numbers for its range, and this can be either finite or infinite. Right. So, the model provides for any precision in length measurements, right. So, why not discrete? Means why we are trying to say that they are going to take the value only inside an interval? Because the number of possible values of x is uncountably infinite, and x has a distinctly different distribution from the discrete random variable. Right. You cannot say that the volume of the shampoo in the bottle is 374 ml or 375 ml or 376 ml, or you say that there cannot be a volume whose value is 375.3 milliliter, right. Okay. So, now we try to discuss here some standard probability distribution of say continuous random variable, or actually they are actually absolutely continuous random variables, right. And the characteristics of continuous random variable are that the number of possible outcomes is uncountably infinite, and that they have a continuous distribution function capital Fx, KDF, right. So, it follows now from the definition of this continuous random variable that the point probabilities are 0, that is the probability that x equal to small x is always equal to 0, that we already have discussed earlier when we try to discuss the discrete and continuous random variables. And we also assume that a unique density function small f exists such that capital Fx is equal to minus infinity to x f t dt, right. So, now we try to take our first probability density function, which is defined for a continuous random variable, and we start our discussion on continuous uniform distribution, right. So, the first question comes here that as soon as I say the name of a new probability function, probability density function now, where it is going to be applicable or under what type of conditions we can use it. So, do you remember the discrete uniform distribution? And we had discussed a couple of applications over there, and practically we assume that the probability of the event at every point remains the constant. The same thing is applicable in this case also. We assume that if our random variable is going to take the value in some finite interval, say a to b, then the probability of the event in this interval remains the same at every point, right. So, that is the basically idea. So, all those experiment, all those situations, all those real life condition where you feel that the probability of occurrence of the event remains the constant in a particular interval, then we can employ there the continuous uniform distribution. So, now the question is, how are you going to represent such a phenomena through a mathematical function, and what are its properties, how it will look like. So, exactly in the same way as we have done in the case of probability mass functions, we will also try to attempt the continuous uniform distribution and other distributions also. Okay, so, let us now try to see how are we going to define the continuous uniform distribution, right. So, a continuous random variable x is said to follow a continuous uniform distribution in the interval, say closed interval a to b, if its probability density function, which is abbreviated at PDF, is given by f(x) equal to 1 upon b minus a if x is lying between a and b are inclusive, because we have a closed interval here, right, and it takes value 0 at all other points, right. And we write this random variable to follow a uniform AB distribution like this: x follows uniform, and inside the parenthesis the values a to b, right. And if you try to plot such a curve, it will look like here you have a point A, here you have here a point B, and now between this A and B you can see that you have here the straight line. So, the probability at every point is just 1 upon b minus a. So, now in case if you find the mean and variance of this random variable x following a uniform AB, they are obtained as expected value of x is going to be a plus b upon 2, and variance of x is going to be b minus a whole square upon 12, right. Well, I am not giving you here the proof, but the proof is very simple. You simply have to just find out the simple integrations and use them in the formula for mean and variance. Right. Now, before I try to take any application, let me try to give you a very important application of this continuous uniform distribution. Many of you might be thinking that, okay, this type of probability density function which has got a constant probability will not have a utility in the real application, but now I am trying to show you here that this is the backbone of the simulation. You try to generate random numbers from different distributions. You already have taken a couple of examples that you use the commands in R software to generate the random numbers from Bernoulli distribution, binomial distribution, uniform distribution, and geometric distribution, and so on. But how are they coming? What is the rule behind them? What is the process? What is the formula that is being used to generate those random numbers? And when you are going to handle the probability density function for the continuous random variable, then also we will try to generate the random numbers. So, how they are going to do? And in this case, this result which I am going to show you, that helps. So, the result says let capital U be a uniform 0 1 random variable, that is any number between 0 and 1, that is U is a number from uniform 0 1. Now, the result is very important. For any continuous distribution function f, the random variable x defined by x which is equal to f inverse u has distribution function f, and this means here what? If you try to see what you have done, you are trying to generate here a uniform 0 1, that means any number between the interval 0 to 1, and then you are trying to use the distribution function or the inverse of the distribution function to find out the value of x, and then x has got a distribution which is different from uniform 0 1, right. So, that is going to give you a random number which is coming from the probability density function which x is following. So, yeah, means obviously here I am trying to use here the mathematical operation f inverse u. So, this f inverse u is defined to be the value of x such that f x is equal to u, right. So, this result is called as inverse transformation method, and this helps in generating the random numbers from a given distribution. So, let me try to take some example here so that I can show you that what I am trying to say through this result. It will become clear. Suppose we want to generate a random number from a probability density function whose CDF is given by like this: f x is equal to x raised to the power of n, and x is lying between 0 and 1. So, we want to generate the random numbers for this random variable x, right. So, suppose we say that x is equal to f inverse u, then what will happen? U is equal to f x, and f x is given to be here x raised to the power of here n. So, obviously, now using this result u is equal to x raised to the power of n, I can write down here x is equal to u raised to the power of 1 by n. This means what? We can generate such a random variable x by generating a random number u and then setting x equal to u raised to the power of 1 upon n. This means what? Suppose I generate a uniform random number, and suppose this is a value between 0 and 1. Suppose this value comes out to be 0.5. So, now in this case, if I try to substitute here 0.5, and then I get here x is equal to 0.5 raised to the power of 1 upon n. Right, and now it means n is going to be some known value, and then you can obtain this number, and this number is not going to be 0.5, but this is going to be something else, right, and this number is denoted here as the one of the possible values of the random variable capital X. So, this value will be treated as if this is generated from a distribution function, this one, f(x) equal to x raised to the power of n, right. So, u is coming from uniform 0 1, but x is coming from this f of x, right. So, that is the advantage. Now, similarly, if I try to take here one more example, suppose we want to generate a random number from an exponential distribution. Well, we are going to study about it in the forthcoming lecture, but at this moment you can simply assume, or I can inform you that the CDF of exponential distribution with rate 1 is given by this mathematical function f(x) equal to 1 minus exponential of minus x. Now, we want to generate a random number from this probability density function, but we do not know how to generate it. So, what we try to do? We try to generate here a uniform random number. Uniform random number means this is lying between 0 and 1. So, it can be any value between 0 and 1. Now, suppose x is equal to f inverse u. This means u becomes equal to 1 minus exponential of minus x, right. And from here I can obtain here x is going to be minus log of 1 minus u. So, now what I have to do? Suppose I want to generate here 5 observation. I simply have to generate 5 values of u, say u1, u2, u3, u4, u5, which are all are lying between this interval 0 to 1, and you simply try to substitute those values here in place of u and compute the value of x. So, this will give you the value, say x1, x2, x3, x4, x5. So, what is happening? That u1, u2, u3 they are coming from uniform 0 1, but these values x1, x2, x3, x4, x5 they will be coming from this distribution function or the exponential probability density function with rate 1, right. So, this is what I am trying to write down here. For example, if you try to choose here u is equal to 0.5, then the value of x is going to be log of 1 minus 0.5. Whatever is the value, that will be the value as if this is generated from the exponential distribution with rate 1. So, this is the advantage of this result. So, I hope I am clear. Right. Now, let us try to take one simple example to show you how the things are going to work, and the same probability I will try to implement or try to find out through the R software. So, that is the same example that we had considered earlier also. Suppose there is a train, this arrives at an interval of 20 minutes at a railway station. Now, if a passenger arrives at the station without knowing the timetable, then the waiting time to catch the train is uniformly distributed with this density. Now, you can recall that you have done this example, but at that moment you have taken it to be k, and then you have found the value of k such that this becomes a probability density function, and you had obtained the PDF as f(x) equal to 1 upon 20. At that moment I have not told you that this is simply the uniform probability density function, but now I can share with you that we had found the probability density function of the uniform random variable. So, this is going to be like this, that when x is lying between 0 and 20, the value of f(x) is 1 upon 20 and 0 otherwise. Now, from this random variable, you already have found its mean, variance, etc. But now we try to compute different types of probabilities. The probability of waiting for the train between say 5 and 7 minutes. So, in order to find out this probability, what are you going to do? You are simply going to find out this interval, probability that x lies between 5 and 7, which is the integral from 5 to 7 fx dx, fx is 1/20, and you can solve this integral, is coming out to be 0.1. So, the probability of awaiting the train for say between 5 to 7 minutes is just 10%, right. And similarly, if you want to find out the probability of waiting for the train between 2 and 18 minutes, then the probability that x is lying between 2 and 18 is the integral to 2 to 18 1/20 dx, whose value come out to be 0.8. So, now you can see whether these two statements makes any sense or not. You are trying to say that the probability of waiting between 5 to 7 minutes is just 10%, and probability of waiting between 2 and 18 minutes it is 80%. Do you think that is it a very realistic statement? Definitely yes, because the train is coming after every 20 minutes, and you are trying to say, well, if you reach a station and you may have to wait between 2 and 18 minutes, what are the chances? Yes, the chances are very high that you will get the train after that, right. So, you can see here that whatever the probability density function you have formulated, whatever the type of probabilities you are trying to compute, they are making sense. Okay. So, now and in case if you try to plot this these two probabilities on the uniform distribution, you can see here, this is here the point 0 and 20. So, this is your here PDF, and now you are trying to say the probabilities between probability of x between 5 and 7. So, this is the area, this is the blue area that we are trying to compute. And similarly, when you are trying to compute the probability that x is lying between 2 and 18, this area is this much, you can see, right. So, obviously, you can see that this area is larger than what? This area. So, obviously, that is making sense, and that is according to what we expect. Now, already have done, but in case if you want to find out the average waiting time, that will be a plus b upon 2, that will be 20 plus 0 upon 2, which is 10 minutes. Right. Now, if you want to compute the probability of waiting for the train for less than 5 minutes, then this can be obtained by computing the probability that x is less than or equal to 5, and now you know this is nothing but your CDF at value 5, and this is equal to integral 0 to 5 1/20 dx, which is equal to 0.25. So, now I try to show you here how you can compute or handle this uniform distribution in the R software. So, here there are two parameters which are going to characterize the distribution, which are min min and max is max. So, they are going to indicate the lower and upper value of the range of x. So, for example, minimum in our notation is going to be A and maximum is going to be here B, because you have taken the symbols as uniform AB. So, now in case if you want to compute the density, you have to use the command dunif. Dunif means D means density and unif means UNIF is indicating the uniform. Right. Now, whatever point at which you want to compute the density, this is here x, and then the minimum value, for example, the default values are 0 and 1, but otherwise you can take here any value here A and B. Right. Similarly, if you want to compute the CDF, you have to use the command punif, and then you have to give here the value q, for which you want to find out the CDF, and then the value of minimum, maximum, and then lower dot tail equal to true, right, that you know how to use it. We have used it earlier. And if you want to find out the quantile function, this is q unif. So, here also you have to give the value at which you want to compute the quantile, and then the minimum value, maximum value, which are the value of A and B, and then lower dot tail equal to true. And similarly, means if you want to generate the random numbers from this uniform AB or uniform distribution, you have to use the command here runif, right, which is equal to here n minimum maximum. That means it will give you small n numbers in the range between minimum and maximum, right. And these are the values which I just explain you, and you can see here that they are the similar what we have done earlier in the case of probability mass function. For example, this lower dot tail, if you try to use it as true, this is going to compute the probability x less than or equal to x, but if you try to make it false, then it will compute the probability x greater than x, right. So, now let us try to solve the same example that we have done, and but now we are going to use the R software to compute different types of probabilities, right. So, our now this PDF is given by 1/20 when x is lying between 0 and 20 and 0 otherwise, and we want to find out the following probabilities: probability of waiting for the train for less than 5 minutes, for more than 6 minutes, between 5 and 7 minutes, and between 2 and 18 minutes. So, how you can find out in the R software, but before that let us try to create this curve, that how this uniform 0-20 will look like. So, for that you can see here I am using the command here curve CURVE, and then I am trying to get the densities of uniform distribution with the minimum value as here say 0 and maximum value here as say 20. And yeah, means on the x axis I am trying to take the value here -3 to 25. For example, this is here -3 and this is here 25. And then on the y axis I am trying to take here the title as density, and the main title here is uniform density function, which is here. So, now if you try to execute this command on the R console, you will get here this type of curve. So, you can see here that between this and this value here is like this 1/20 minus 0, right. And here you can see here and here, when the x values are less than 0 or greater than 20, then this value here is 0. So, you could see now using such a command you can very easily create the curves of the probability density function. I will try to show you on the R console also, but let us try to first understand how are we going to compute different types of probabilities. So, now you know that using this command punif you can compute the CDF, right. So, now suppose we want to find out the probability that x is less than or equal to 5. So, this can be written as CDF at the value 5, and if you want to solve it, this will come as 0.25, that we already have done, but now we try to find out this probability directly using the R. So, I try to use here the command punif, and I try to write down here 5. This 5 is the same 5 here, and then the minimum value of this range is 0 and the maximum value is 20, that is A is equal to 0 and B equal to 20. So, now if you try to execute it, it will give you the same value 0.25, and this is the same what you have obtained here. And yeah, means if you want to use here the option lower dot tail is equal to true, even then you will get the same value here, that you know. So, and this is here the screenshot of the same probability, right. And similarly, if you want to find out the probability of waiting for the train for more than 6 minutes, that means you want to obtain the probability x greater than 6, which is can be written as 1 minus probability of x less than or equal to 6, which is 1 minus the value of CDF at 6, and this can be solved as 0.7, right. So, this probability can be obtained by here 1 minus punif at x equal to c. So, this 1 is corresponding to this one, and this 6 is corresponding to this 6, right. And then these are the uniform distribution range, and this value will come out to be 0.7, and you can see here this is the same value that you had obtained through the algebra. And well, in case if you do not want to use this business of 1 minus f of 6, then this probability, that probability x greater than 6 can be obtained directly by using here the command lower dot tail is equal to false. So, you try to use the same command, but you try to make it here lower dot tail is equal to false. This will give you here the same value, and this is here the screenshot, right. So, you can see here it is not difficult to compute such probabilities, and if you want to compute the probabilities of waiting for the train between say 5 and 7 minutes, this probability can be computed by say x lying between 5 and 7. So, that will be integral 5 to 7 1/20 dx, and this value can be solved to be 0.1. And in case if you want to find out this probability using the R software, then this probability can be written as here f7 minus f5, that means the value of CDF at 7 and 5. And now you know how to write down this f7 f5. So, f7 can be written like here this, and f5 can be written here like this, right. And if you try to solve it, you will get here the value 0.1. This is the same value that you are getting after solving it mathematically, right. And similarly, if you want to compute the probability of the train waiting time between 2 and 18 minutes, exactly you have to do the same thing, probability that x lies between 2 and 18, that will be integral from 2 to 18 fx dx, and this value can be solved to 0.8, and this probability can be expressed by f18 minus f2. So now you can use the same command over here, that this is the command for f18 and this is here the command for f2, and this value will come out to be 0.8 here. So you can see here in this exercise that you can compute this probability, but what will happen if you don't know this part? Can you compute the probability? No. So here comes the statistical knowledge, that how are you going to express this probability and how are you going to find it out, and that will help you inside the R software, that what exactly you have to do, right. And similarly, if you want to find out the quantile, then you have to use here the command. If you want to find the percent quantile of the same PDF, then this can be obtained by using the command q unif and p is equal to 0.6 and minimum equal to 0, maximum equal to 20, and this will give you here the value 12. And in case if you want to use here the option lower dot tail is equal to true, then it will give you here the value of this quantile as 12, same thing, right. And similarly, if you want to generate say random numbers from this uniform distribution, then you know exactly you have to go in the same way as you have done in the past. You have to use the command here runif. So now suppose if you want to generate 5 numbers from the uniform 0 to 20 distribution, then it is going to be runif n is equal to 5, minimum is equal to 0, maximum equal to 10, and this will give you here 5 numbers, and you can see here all these numbers are lying between 0 to 20. And surely if you want to repeat this experiment, do you think that are you going to get the same thing? Certainly not, because these are the 5 random numbers between 0 and 20, and if you want to repeat it, they will give you some other value. So I think before going further, first we try to just try to see whether you can do these things in the R console or not. So let me try to first plot this curve, right. So you can see here, clear the screen, and let me try to make the screen little bit shorter so that you can see the graph also. You can see here now, this is the same graph that you have just obtained. So it is not difficult. And similarly, if you want to generate here any graph, say here between say here 10 to 20, right, that also you can see. You can see now this area is shifted, this is now between 10 to 20, right. So at least you can view that how this graphs will look like. And now if you try to compute the same probability, so you can be confident that if you try to write them here, you are getting here the value 0.25, and this is the same value that you have obtained here. So you can believe on me, whatever I have shown you, this is really working. And if you try to see here in this example, the probability is coming out to be same as 0.7, and instead of this 1 minus fx, if you want to find out the probability directly from here, you can see here that can be obtained by this thing, right. The values are going to be the same in both the cases. And similarly, if you want to compute the other probabilities like this one, which you have here, you are trying to compute the waiting time between 5 and 7 minutes, you can find it out. This is 0.1, and this is the same value that you have obtained here, right. So, and then if you want to find out the value between say here the waiting time to be between 2 minutes and 18 minutes, then this command can be obtained here like this, right. Minimum and maximum is equal to 20, right. You can see here 0.8. And similarly, if you want to find out the quantile, the 60th percentile or 60th quantile of this uniform 020, you can see here this is coming out to be 12, what you have obtained here, right. And similarly, if you want to generate here the random numbers between 0 and 20, say suppose we want to generate 5 numbers, they are coming out to be here like this. And similarly, if you want to repeat this experiment, it will give you one more set of 5 random numbers. And if you want to generate here more random numbers, suppose you want to generate here 15 random numbers, it will give you 15 values between 0 and 20. Right. So, you can see here now computing and executing these commands in the R console is no more difficult for you. They are very simple thing. And now for this uniform 0, 20, if you try to compute the mean and variance, the mean and variance are here 10 and 33.33 respectively. And if you want to see the behavior of this random numbers or the number of random values that when you are trying to draw them on the basis of a sample, how they are getting closer to the theoretical mean and variance, then you simply try to generate here some random numbers, say 100 or 10,000 random numbers, and you try to find out their mean and variance. Well, I have already shown you a couple of times. So, this is the same exercise. So, suppose I try to generate only here a number of observations from uniform 0, 20. The true value of mean and variances are 10 and 3.33. But if you try to compute the mean based on 10 observation, that is coming out to be 13.54, 10.72, 8.28. You can see that this is varying, right, and the variance is coming out to be 11.5, 42.3, 30.58, right. So, there is a lot of variation, but if you try to increase the number of observations to 1000, you can see here the value of means are coming out to be 9.95, 9.87, 10.06, which are more closer to 10 than the earlier case, and the variance are coming out to be 33.37, 33.48, 33.87, which are getting to be more closer to the 33.33. And in case if you try to increase the sample size more, possibly you will get better values. So, now these are the screenshot of the same operation which I have shown you here, right. So, now we come to an end to this very interesting lecture. That was a very simple lecture, but very useful. Now, you have learnt one result that is going to lay the foundation of the all simulation that we are trying to conduct, right. So, now I will make you the same request that I make after every lecture, that now you have understood what is this uniform distribution. Why don't you take some example from your assignment books and try to do them, try to compute some probabilities and try to compute the same probabilities in the R software also, and try to see whether those theoretical probabilities and those probabilities that you are trying to compute inside the R software, whether they are matching or not. You see, now you must be very comfortable in implementing the R software in computing these various types of probabilities. But the main challenge is this, how to compute this probability, whether you want to take the summation or integral with what limits, where you have to write down the PDF, CDF, etc. For that you need the theoretical background, basic fundamental, that how to compute the probability using PDF, CDF or distribution function. Or if you want to compute something else, you can even compute the CDF empirically also. This is called as empirical CDF, ECDF. All those things are possible. Now you are in a stage where now you can think and can experiment yourself also with different types of concept in statistics that we are trying to implement here and learn. So, you try to practice it, and I will see you in the next lecture. Till then, goodbye.